Good day, everyone. So we're reviewing Wetzel's Limnology textbook. This is edition number 4, and we are focused on chapter 13, which deals with dissolved inorganic carbon. And today we are looking at dissolved organic carbon sources. And let's get started. This is where we left at yesterday. The carbonate ion can also be in solution and enter from upstream and from groundwater if the dissolved inorganic carbon, or DIC, and or the pH are high enough. Further, carbonate can be produced by reverse weathering, for example, equation 13-12. This occurs during the drawdown of CO2 during intense periods of primary production. If the resulting concentration of calcium carbonate is high enough, it will precipitate as the solubility of calcium carbonate is not large. Fine particles of calcium carbonate can form whiting events, which are common in productive hard water lakes. These whiting events can even be tracked by remote sensing and even by satellite in very large lakes. Somewhat counterintuitively, the precipitation of calcium carbonate represents a source of CO2 into the water column, just as the dissolution of calcium carbonate is a sink for CO2. Some freshwater organisms make shells of carbonate, notably snails and freshwater mussels. It is intriguing that freshwater pelagic organisms with carbonate shells are very rare in lakes, whereas in marine systems they are common. For example, coccolithophorids are very common in the ocean and absent in freshwaters. Many macrophytes will precipitate calcium carbonate as marl on their exterior during photosynthesis. The microalgae chara is often seen with calcium incrustations. It is interesting that even in very soft freshwaters, there can be perfectly healthy populations of benthic mussels and snails. For example, Strayer found that the unionid clam Elyphthocomplanata had normal growth rates in Mirror Lake, which has an ANC of less than 70 microequivalents per liter and pH between 6.5 and 7. Calcium carbonate can also be found in colloidal form. The importance of these is poorly understood. Wetzel reviewed the literature on this topic, which was mainly old and has not been seriously followed up. The major importance of this is that the organic coatings reduce the rate of dissolution of sedimenting calcium carbonate in lakes and can form a major sink for inorganic and organic detrital carbon in hard water lakes or ecosystems. C. Alkalinity, acidity, and pH of natural waters. Alkalinity. Natural waters exhibit wide variations in relative acidity and alkalinity, not only in actual pH values, but also in the amount of dissolved material producing the acidity or alkalinity. The concentration of these compounds and the ratio of one to another determine the actual pH and the buffering capacity of a given water body. Since the lethal effect of most acids begin to appear near pH 4.5 and of most alkalides near pH 9.5, that buffering can be of a major importance in the maintenance of life. Alkalinity is historically a term that referred to the buffering capacity of the carbonate system in water. The terms alkalinity, carbonate alkalinity, alkaline reverse, titratable base, or acid binding capacity are frequently used to express the total quantity of base, usually in equilibrium with carbonate or bicarbonate, that can be determined by titration with a strong acid. The milliequivalents of acids necessary to neutralize the hydroxyl carbonate and bicarbonate ion in a liter of water are known as the total alkalinity. Alkalinity is numerically the equivalent concentration of titrable base and is determined by titration with a standard solution of a strong acid to equivalency points dictated by pH values at which the alkaline contribution of hydroxide, carbonate, and bicarbonate are neutralized. The term hardness is frequently used as an assessment of the quantity of water supplies. The hardness of water is governed by the content of calcium and magnesium salts, largely combined with bicarbonate and carbonate, and with sulfates, chlorides, and other anions of mineral acids. The carbonate hardness can be removed by boiling, which causes the precipitation of calcium carbonate. The fraction of calcium and magnesium remaining in solution as sulfates, chlorides, and nitrates after boiling constitutes the residual non-carbonate hardness. The extent of hardness has been expressed numerically in a remarkably heterogeneous system of scales among different countries. When water is hard, it causes problems for plumbing, pipes, hot water heaters, and coffee makers, among other issues. This is why many homes need to use a water softener to lengthen the life of plumbing and appliances. Limnology still sometimes categorize lakes as hard or soft water systems. Alkalinity is now used interchangeably with acid neutralizing capacity, or ANC, which is the capacity to neutralize strong inorganic acids. ANC is the amount of acid that it would take to move a water sample from its current pH to reach a pH corresponding to a solution of pure CO2, which is near pH 4. Another way to say this is that ANC is the amount of acid required to convert all the DIC, dissolved inorganic carbon, to carbon dioxide. One can write a long chemical equation to describe alkalinity that includes all of the acids and bases that might be in the water sample. In most natural freshwaters, the simplified equation below is sufficient where the carbonate system totally dominates ANC. So ANC is equal to bicarbonate plus 2 carbonates plus hydroxide minus protons. ANC is expressed in units of microequivalents per liter. A low ANC system would have ANC less than approximately 50 microequivalents per liter, and a high ANC would have values greater than 2,000 microequivalents per liter. Measurement and calculation of alkalinity and DIC. In the older literature, alkalinity was usually expressed in unit of calcium carbonate per liter. Thus, limnologists measured alkalinity by titration with acid and expressed it as if all the carbon was in the carbonate anion and calcium was the cation. Since the later half of the 20th century, DIC is typically measured by either gas chromatography, or GC, or by a dedicated infrared gas analyzer, IRGA. After all forms of inorganic carbons are converted to CO2 by acidification. Correspondingly, in modern literature, ANC is calculated from direct measurements of pH and measurements of DIC. Dissolved organic compounds are also a weak source of alkalinity, typically 1 to 3 microequivalents per milligrams of dissolved organic carbon. When carbonate alkalinity is very low, less than 50 microequivalents per liter, however, these organic acids can constitute a significant fraction of the total alkalinity. Properties of alkalinity. ANC has some useful properties. For one, unlike total DIC, it is unaffected by changes in CO2. This makes ANC relatively conservative, especially in oxic surface waters. Further, pH is affected by changes in CO2. Thus, in many systems, one can take continuous measurements of pH and use these to calculate the changes in CO2 if ANC holds relatively constant. These changes in pH also can be used to calculate ecosystem metabolism under the right conditions. There are some reactions that generate or consume ANC. Obviously, the addition of acids lowers it. Acids can also be generated by the oxidation of iron or sulfur compounds. Several processes can generate ANCs. These include the uptake of nitrate by phytoplankton and nitrate and sulfate reduction in anoxic waters, among others. These reactions that change ANC tend to be relatively small compared to ANC in most systems, especially in surface waters. On the other hand, ANC, which is once again acid neutralizing capacity, can increase over depth, sometimes greatly, if there is sufficient anaerobic respiration, as several types of anaerobic respiration generate ANC. Alright, so let's review Table 13-2, some of the key aerobic and anaerobic respiratory pathways in inland waters and their effect on ANC. Aerobic respiration, methanol plus oxygen is equal to carbon dioxide plus water. No change in ANC. Type of organisms, aerobic bacteria, algae animals. Aerobic methane oxidation. Methane plus 2 oxygen is equal to carbon dioxide plus 2 waters. No change in ENC. Methanotrophic bacteria such as Methylocystis. Anaerobic respiration. Nitrate reduction. Methanol again plus 0.5 nitrate is plus 0.5 water is equal to 0.5 ammonium plus bicarbonate. That increases the ENC. The denitrifying bacteria such as Pseudomonas is an example of it. Sulfate reduction, ethanoic acid plus sulfate plus 2 proton is equal to hydrogen sulfide plus 2 bicarbonate plus 3 proton. That increases the ANC, and sulfate reducing bacteria such as disulfovibrio is an example of that reaction. Iron reduction, we have a carboxylic group plus 2 ferric plus water is equal to bicarbonate plus 2 ferrous plus 2 proton. That increases the ANC. Iron reducing bacteria is an example, such as Geobacter. Methanogenesis, acetoclastic, such as fermentation. We have ethanoic acid or acetic acid is equal to methane plus CO2, no change in ANC. Methanogenic bacteria such as Methanosarcina and Methanobacterium. Secondly, there is a great deal of historical data with measurements of alkalinity, some also with pH, and some going back nearly 100 years. Raymond et al. Used archived USGS data to show that the export of alkalinity by the Mississippi River has been increasing over the past century. Further, there is a great deal of alkalinity and pH data from regions of the world where direct DIC measurement has not been routine, and from field stations that do not have the most modern equipment. These data, along with temperature, have been instrumental in revealing patterns about both DIC and partial pressure of carbon dioxide in surface waters of lakes, rivers, and streams. Acidity. Acidity is used infrequently as a parameter in limnological investigations. In practice, acidity is a measure of the quantity of a strong base per liter required to attain a pH equal to that of a solution of sodium carbonate, Na2CO3, equivalent to the total inorganic carbon. Like alkalinity, it is measured by titration. As such, acidity is not particularly useful. On the other hand, H+ is both a useful and necessary parameter. Hydrogen ion activity and pH. In practice, it is common to use the term acidity rather interchangeably with pH, even though this is not strictly correct. When limnologists talk about acidic water bodies, they mean water bodies with high levels of hydrogen ion activity. We cannot directly measure protons. Instead, we can measure hydrogen ion activity. This is what is actually measured with a pH meter. pH is equal to minus log 10 of the hydrogen ion activity. In the above equation, the H+ term comes from pH measurements, and we write it as the concentration of H+. All of the constants in the carbonate system equations were determined in reference to pH measurements, for example, hydrogen ion activity. So the system is completely consistent. Pure water dissociates weakly to protons and hydroxide ions. The dissociation constant is very small, approximately 10 to the minus 14. However, and the amount of H+ and hydroxide presents are 10 to the minus 7 mole per liter. Natural waters are of course not pure, and salts, acids, and base contributes to the H+ and hydroxide ions in varying ways depending on the individual circumstances. Since the dissociation constant of water is fixed, the addition of one ion will result in a decrease in the other. The pH is defined as the logarithm of the reciprocal of the concentration of free hydrogen ions. The P of pH refers to the power, from the French term puissance, of the hydrogen ion activity. Therefore, more H+ activity in an acid reaction increases the power from neutrality in 10 to the minus 7 or pH 7 to say 10 to the minus 4, pH 4. In more alkaline solution reactions, H+ ion activity is decreased from neutrality to, for example, 10 to the minus 10, pH 10. Range of pH in natural waters. The pH of most natural waters ranges between the extremes of pH less than 2 and 12. Nearly all natural unpolluted waters with pH values less than 4 occur in volcanic regions that receive strong mineral acids, particularly sulfuric acid. Some of these lakes are extremely acidic. For example, a crater lake in Indonesia has a remarkably low pH of about 0.3, which is much more acidic than the most acidic soft drink. The oxidation of pyrites, of rocks, and clays in drainage basins can result in sulfuric acid drainage to lakes. Several acid mine drainage lakes in China have a pH in the range of 2 to 3. Moderately low pH values are often found in natural waters rich in dissolved organic matter with low amount of DIC. An appreciable portion, greater than 50% of dissolved organic matter, occurs as organic acids derived from humic compounds, which are comprised of a large number of complex ligands that have numerous pK and charge density sites. Charge density means the number of sites per mole of carbon. The carbon of organic acids varies from 5 to 22 microequivalents milligrams per carbon, often with an average of carboxylic acids of approximately 10 microequivalent milligrams per carbon. Organic acids can modify both the acidity of surface waters and changes in strong acid inputs in water with low or little bicarbonate alkalinity. Organic acids may depress pH by 0.5 to 2.5 pH units in waters with A and C range of 0 to 50 microequivalents per liter. Despite these direct additions to acidity, organic acids have a substantial buffering capacity for strong acids and can reduce pH fluctuation from strong acids in precipitation. Low pH values are particularly common in bogs and bog lakes that are dominated in the littoral mat by the moss sphagnum. The pH of sphagnum bogs is usually in the range of 3.3 to 4.5, 0.5 to 0.03 microequivalents of H+ per liter. The sources of the H+ ion activity are several. The metabolism of proteins and the reduction of sulfate by sulfur metabolizing bacteria may contribute some H+ ion to these waters, but their contributions are likely to be small. Although live sphagnum plants secrete organic acids, concentration of these acids are usually insufficient to account for the observed acidity. Most of the H+ ion concentration appear to result from the active cation exchange by the cell walls of sphagnum, during which H+ is released. Another cause of acidified lakes and streams is acid rain, or more correctly referred to as acid precipitation, as it includes snow, sleet, and other forms of precipitation. The emission of sulfur and nitrogen from the burning of fossil fuel and high temperature combustion produce sulfuric and nitric acid, which the precipitation returns to Earth. We think of pure water that is neither acidic nor basic as having a pH of 7. Rainwater is naturally acidic because it is in equilibrium with atmospheric CO2. The pH of rain in a pristine atmosphere at current CO2 level is about 5.6, but can be below 4 in polluted areas, so quite acid. In poorly buffered areas that receive this rain, the lakes and streams reflect that acidity. For example, in the Adirondack region of New York State, and in areas of Quebec, Canada, and Sweden, many lakes and streams have had pH values well below 5. Much controversy has arisen over the natural versus the anthropogenic components of the acidification of natural waters. In remote areas, natural processes can dominate. These include complex humic and other organic acids, for example, from bog drainage, as well as proton ions or H+ ions generated from the nitrification of ammonium, manganese oxidation, ferrous iron oxidation, and sulfide oxidation. However, the overwhelming loading of acidity to sensitive surface soft waters has resulted from anthropogenic pollution from fossil fuel combustions and the production of proton or H+ ionized from several strong acids. With stronger regulations on the use of high sulfur coal as well as other acidic emission, pH values of lakes and rivers are recovering slowly from peak acidity. Another major source of anthropogenic acidity is acid mine drainage, which is caused by the oxidation of reduced iron and sulfur compounds that are brought up to the surface during the mining of coal and other minerals. When these oxidize, they can cause extremely low pH in the waters that drain them, and if this water finds its way into lakes and streams, it can result in strong acidification. The highest pH values in lakes are usually found in endorheic regions where lake waters contain exceedingly high concentration of sodium carbonate, and are therefore often referred to as soda lakes. For example, highly saline soda lakes include Mono Lake, which has a pH of about 9.5, and lakes Nakuru and Bogoria in Kenya, which have pH values above 10. The range of pH of most open drainage lakes is between 6 and 9. Most of these lakes are the bicarbonate type. That is, they contain varying amount of carbonate and are regulated by the proportions of carbon dioxide, bicarbonate, and carbonate in the water. Calcareous hard water lakes commonly are buffered strongly at pH values greater than 8. Seepage lakes and lakes within igneous rock catchment areas are less well buffered and are more acidic, with pH values usually somewhat less than 7. And that concludes today's session, and I appreciate your attendance, and I will see you tomorrow, and we'll start next section tomorrow on CO2 carbon dioxide dynamics. Thanks, and have a good day. Bye.